I know what we should do. Let's make a video about relativistic energy and general relativity. Alright, today we're going to talk about the big one. E equals mc squared. Everybody quotes it. Very few know what it means. Alright, so today we're going to dive into what E equals mc squared means, and then I'm going to talk to you a little bit about general relativity. There's no homework on general relativity, but it's fun. You need to see it because you have to have that aspect to your life. So I'm going to go over that quickly, but first, the big E equals mc squared. What does this mean? Where does it come from? Well, here's the basic idea. Imagine this. Imagine you are looking at an ideal train car sitting on an ideal frictionless train track with frictionless wheels, whatever, right? And you look at that train car, there are no external forces acting on it in the x direction. But then suddenly it moves. And you're like, whoa, things can't just accelerate if there's no force acting on it. And then you start to realize, and you say, oh, wait a minute. If this train car is like a closed system, if no forces act on it, its center of mass can't change, but it can rearrange its mass inside of it, right? Things happening inside the car can rearrange the center of mass. For example, imagine you had a baseball pitcher who threw a very heavy anvil from one side of the car to the other, right? When they throw the anvil, they put momentum into the anvil, so the anvil pushes back with an equal and produces an equal opposite momentum on the baseball player and the train car. The anvil flies forward, the train car flies backwards, then the anvil hits the side of the wall, and they both come to a stop. All right? So no external forces acted on the train car. However, the train car moved. But the center of mass of the system didn't change. All right? So that's the big deal. All right? So I had this train car, and it had a mass. Let's say it had a mass capital M. All right? Initially, the center of that train car's mass is at 0. All right? But then we moved this anvil. All right? We moved some mass from one side to the other. All right? So the anvil. So initially, we have a mass distribution, but then we move the anvil to the other side of the car, right? And so now the center of mass within the car is going to move over a little bit, right? But if we want that center of mass not to move because there's no external forces acting on the cart has to move then that way to keep the center of mass fixed. So in order to not violate the laws of physics, the car must move. That's the idea. Okay, so now this is what Einstein's imagining, something like this. He says, imagine, well, okay, he had a very different scenario, but this is like what he thought. Imagine, if you will, I have a light bulb, right? And I use some energy to create a photon of light, or some mass, maybe not a photon, maybe a bunch of photons, some little pulse of light. And that light shoots away from the light bulb. Now, light carries momentum. We know that. That's not relativity, that's classical electromagnetism, all right? We know that if I have some energy worth of light, I put some energy into light, it will carry a momentum which is equal to its energy divided by c. That's from classical electromagnetism, all right? So if this light starts flying off in this direction, that means it's carrying momentum, all right? So conservation of momentum says that the train car then has to recoil in the opposite direction, right? Equal and opposite forces equal and opposite momentum. All right? And then the light hits the other side, gets absorbed, the train absorbs that momentum again, and the train car comes to a stop. Okay? So the light's gone. The light didn't exist. I made it, and then it disappeared. Right? That light turned into heat or something. It was absorbed. That energy was absorbed by this wall. But in the process, the train car moved a tiny, tiny little bit. All right? So Einstein's thinking about problems like this, and he says, this energy, right, the light carried the momentum, but the light didn't exist before the experiment, and it doesn't exist after the experiment. So effectively all we've done is we've transferred some energy from one side to the other. And Einstein says, wow, energy, by transferring energy we also transferred mass. So mass is just a form of energy. All right? And basically doing the derivation, what do? We say, well, look, this train car moved some distance delta x. And I'm going to do kind of a hand-waving derivation with some approximations in it, just to make it simpler. All right? But let's say the train car moves some distance delta x. Well, delta x, how far did it move? Well, that's just velocity times time. How fast was the train car moving backwards times how long was it moving backwards? All right? Well, how fast did it move backwards? Well, I know that the light carried a momentum p, all right, which is the energy in the light over c. All right? The train car, it's moving backwards with that same momentum. But momentum, all right, now I'm going to make my approximation. Remember last time we learned that momentum has this gamma in it, but I'm going to assume that the train car is moving fairly slowly, so that its momentum is approximately the mass of the train car times its velocity. All right? Okay, so that means the velocity of the train car is just its momentum divided by its mass. All right, but its momentum is the momentum of the light, which is the energy in the light divided by c. So this is just E over the mass of the car times c. All right, so there's the velocity I'm going to plug into there. How long? How long did the train car move backwards? It's the same as the time that the light was moving forwards. So the time that the light took to get from one side to the other is just the length of the train car divided by the speed of light. So the distance that the train car moved backwards is just v times t, but v is E over the mass of the train car times c, and t is the length of the train car divided by c. So here we have E times L over mc squared. Oh, mc squared. Okay, we're not there yet though, because this is the mass of the train car. This is not the mass of the stuff that we transferred from one side to the other. All right? To get the mass of the stuff we moved that goes along with the energy we moved from one side to the other, what we're going to do is we're going to say if the center of mass doesn't change, then the mass of the train car times how far it moved must be equal to the mass of that energy that we moved from one side to the other times how far it moved, right? The one moves one way, the one moves the other. Their effect on the center of mass must cancel out, all right? So here's another equation that relates how much the train car moves and its mass to the mass that goes along with the energy that we moved. All right? Well, we have delta x here, so let's plug it in. So we have capital M times delta x, which is the energy in the light, times L over mass of the train car c squared, and that's equal to the mass that was transferred by the light times L. Notice the L's cancel out, the M's cancel out, and if I move the c squared to the other side, I get E equals mc squared. So there's the derivation. Kind of long. I hope you were able to pay attention and understand what we were doing. Why is the derivation important? Because it tells us exactly what everything means. What is E? E is a bunch of energy. What is M? M is the mass associated with that energy. So by taking energy from this side of the car and putting it on this side of the car, we've effectively transferred mass from one side of the car to the other. Where did that energy come from? Well, maybe it was chemical energy in a battery we used to make the light bulb light up. Once it gets over here, it gets absorbed by the wall heats up a little bit, maybe it's thermal energy. It doesn't matter what the form of the energy is. By moving some energy from here to here, we've also moved mass from here to here. So I'm going to doctor up this equation a little bit. I'm going to put a little 0 there. That means rest energy, all right? Just to make sure we're not confusing with other types of energy. All right. So if I have a sphere of iron, it's got some mass, right? That means its mass is energy. All right. But if I change the energy, I also change the mass. So imagine, if you will, I take that sphere of iron and I heat it up, and I give it some energy. All right. That energy is not something physical. I've not put new particles into the sphere. I've just heated it up. I put it over the heater. I warmed it up. If its energy goes up, its mass also goes up. All right? And that's what E equals mc squared is all about. And now you know. You're one of the privileged elite that knows what E equals mc squared really means. Okay, a lot of people don't. My daughter had a high school, I think it was a junior high textbook, a math book, where they did a problem where they solved this equation, and they tried to explain what it meant, and they were totally off. They were wrong. But now you know. So I hope you feel special. Okay. What if an object is moving? If an object is moving, in addition to its rest energy, it also has kinetic energy. And it turns out, without actually doing any sort of derivations or anything, we're just going to give you that the total energy of an object is gamma mc squared. But of course, this is I should have put a U on there. This is gamma for the velocity of the object, not transferring into some other reference frame. So the total energy is just gamma times mc squared. All right, but we know that the rest energy is is just mc squared, which means that the kinetic energy must be gamma minus 1 times mc squared. All right, so if I ask you about the kinetic energy of an object, right, classically it's 1/2 mv squared. All right, but in relativity, it's gamma sub u for the object, gamma minus 1 times mc squared. Now this doesn't look anything like 1/2 mv squared. What happens in the limit as the velocity gets really, really small? It should turn back into 1/2 mv squared, right? Or mu squared, I guess, if we're using u to describe the velocity of the object. All right? This doesn't look anything like that, but notice in the limit as the velocity gets really small, as u gets really small, this gets really close to 1, and this goes to 0. All right? That's the kinetic energy right there. You have to do some tricky things with Taylor expansions and stuff to make it all work, but it does turn back into 1/2 mu squared like it should be classically. All right? This is very similar. All right? Remember, we have a new version of momentum. We found last time the momentum is gamma sub u mu. All right? The total energy is gamma mc squared. All right? There you go. So if I ask you to find the total energy of an object, gamma mc squared. If I ask you to find the kinetic energy, gamma mc squared minus the rest energy, mc squared. If I ask for the rest energy, mc squared. All right? Okay. Notice, if I were to plot the kinetic energy of a massive object as a function of velocity, classically, I get a parabola, right? Classically, where'd my cursor go? There it is. Classically, the kinetic energy is 1/2 mass times velocity squared, right? I'm using a u for velocity, right? But quantum mechanics, or sorry, in relativity, the kinetic energy is gamma u minus 1 times mc squared, and as u goes to c, gamma goes to infinity. So this is actually limited, all right? As you approach the speed of light, the kinetic energy goes to infinity. So there's another reason. So here's two reasons why you cannot travel at the speed of light if you have mass. First of all, your total energy and your kinetic energy would have to be infinite. So it takes an infinite amount of energy to accelerate you up to the speed of light. Also, your momentum would be infinite if you're traveling at the speed of light. All right? So it takes an infinite amount of force, or a finite amount of force for an infinite amount of time to get your momentum up to be infinite. So you cannot travel, a massive object cannot travel at the speed of light. Conversely, an object which has no mass can only exist traveling at the speed of light. All right? So for a photon of light to carry momentum, all right, it travels at the speed of light. It means its mass has to be equal to 0. Conversely, if its mass is 0, it has to travel at the speed of light, so that, right, if mass is 0 and gamma is infinity, right, I multiply them together, I can get whatever I want, right? And you take limits. But, yeah, if mass is 0 and the speed is not the speed of light, then gamma is less than infinity and you get 0. Alternatively, if the speed of an object is the speed of light, then gamma is infinity. If the mass is not 0, we get infinite momentum. All right? So a particle that has rest mass, like you or me, cannot travel at the speed of light. We can only approach the speed of light. A particle with no rest mass, like a photon, can only exist by traveling at the speed of light. Groovy stuff. All right, so here, just kind of as an example of how this all works, at the Electron Accelerator in Cambridge, Massachusetts, the final acceleration stage has the following characteristics. So they accelerate electrons up to 0.99986 times the speed of light. And this is old data. This is not updated, so maybe this only used to be true. But consider this old experiment. They get the electrons going pretty fast, and then they put them into the final acceleration stage, which accelerates them up to this velocity right here. All right? Initially, their relativistic mass is 60 times their rest mass. After that final acceleration, it's 11,000 times their rest mass. This increase in velocity requires an increase in energy which is 186 times higher than what it started with. But if you took a car traveling at this velocity and have it travel for 2 hours, if then you took a car that was traveling at this velocity, made it travel the same path as that one, it would take 1 hour, 59 minutes, and 59 seconds. So that huge increase in energy, it only shaves 1 second off of a 2-hour journey. So that's what we're talking about. To increase the energy just a little bit, once we get close to the speed of light, it takes lots and lots of energy, because in order to get this actually all the way to the speed of light, it takes an infinite amount of energy. So it takes more and more energy to increase the speed less and less as the particle moves closer and closer to the speed of light. Now, incidentally, in case this comes up in homework or in exams, a lot of times we'll talk about the energy of particles in terms of electron volts. An electron volt is simply another unit of energy. It's 1.602177733 times 10 to the minus 19 joules is 1 electron volt. Why do we use these units? Because they're very convenient. It turns out that this unit is defined such that if I have an electron and I accelerate it across a potential generated by two metal plates that have voltages that differ by 1 volt, its kinetic energy will be 1 electron volt. That's where that comes from. But if electron volts ever come up, that's how you convert it to joules. All right. Now that's everything you absolutely need to know for the homework. But I'm going to show you some stuff at the end that you don't absolutely need to know that's interesting and cool. This is sort of somewhere in between. You don't need this for the homework, but I really highly recommend that everyone in the class watch this presentation on general relativity. It's going to be very kind of touchy-feely, not very mathematical, just so that you know what general relativity is all about if it ever comes up, if someone ever asks you about it. Plus, it's super cool. Here's the idea with general relativity. So, special relativity ignores gravity. Einstein later comes along with general relativity and says, here's a way we can incorporate gravity into all of this. And the way that he incorporates gravity is he comes up with the equivalence principle. He makes sort of another postulate that says gravity and acceleration are equivalent. That's the equivalence principle. What does that mean? The equivalence principle basically says if I put a scientist in a box, all right, and they cannot communicate with the outside world, all right, they cannot tell the difference between gravity and acceleration. So for example, if this scientist takes a ball and drops it, it will accelerate at 9.8 meters per second squared, right? But now imagine the same scientist is on a rocket that's accelerating at 9.8 meters per second squared. If they let go of a ball, there's no force on the ball, but it appears to them like it's accelerating at 9.8 meters per second. It's as if there was gravity, even though there's not. It's just an artifact of the fact that their reference frame is accelerating, all right? The equivalence principle says there is no way to tell the difference between an accelerating reference frame and gravity, all right? So the equivalence principle says, all right, I drop the ball, I don't know that I'm accelerating, I think I'm on Earth. There's no way to tell the difference. What it says then, that there's, okay, if there's no way to tell that if we are on Earth or in an accelerating spaceship, if the scientist on the accelerating spaceship is not in an inertial reference frame, neither is the scientist on Earth. So if you're standing on Earth, right, we talked, the issue always comes up. Is Earth really an inertial reference frame? We're moving around the sun, so we're accelerating, right? And so you say, okay, well, let's neglect that. Let's say that that acceleration is too small to worry about. There's still another problem. You're not in an inertial reference frame because there's gravity. All right? If the scientist on the accelerating spaceship is not in an inertial reference frame, then neither is the science on the Earth. So how can I do an experiment on Earth in an inertial reference frame? Well, what you have to do is do the experiment in free fall. All right? So if you're standing on Earth and you're feeling gravity, you're not in an inertial reference frame. But if you jump off a cliff, as you're free falling, now you're in an inertial reference frame, right? It's in an inertial reference frame because if I let go of a ball, it just floats there. There's no forces acting on the ball, and it doesn't accelerate. Now you're saying, Dr. Durfee, there is a force acting on it. It's gravity. So the fact that it's not accelerating when there's a force on it means I'm not in an inertial reference frame. Well, no, that's where the equivalence principle comes in. The equivalence principle says gravity's not really a force. All right? Gravity is really just this curving of space-time. And in a truly inertial reference frame, things don't fall under gravity. So in free fall, I'm in an inertial reference frame because gravity and acceleration are equivalent. To get away from an accelerating reference frame, I have to jump off the cliff so that things float and don't fall under gravity. All right? So imagine, if you will, I have two scientists. One is on the Earth and one is up in a tower that's really, really tall. And the scientists down below, they send a beam of light up, a beam of blue light up to the scientist up at the top of the tower. All right? Now, these two scientists are not in an inertial reference frame because gravity is acting on them. So we cannot use our equations for, inertial reference frames to calculate what happens. So instead, we're going to have a free-falling observer that's jumping off of a cliff while this happens. This free-falling observer sees this scientist shoot the laser beam up, and this other scientist detects it. This free-falling observer says, look, by the time, right, when I jumped off the cliff and the light was sent up, they were both sitting still. But by the time the light reaches the scientist up top, right, the free-falling observer is now moving at a good velocity. But really, the free-falling observer, they're the one that's in the inertial reference frame. So let's not think of them as falling. Let's think of these scientists as accelerating upwards. So by the time the light reaches the scientist up here, they're now moving away from the source of the light. And the light will be Doppler shifted. It will be redshifted. So Einstein's equivalence principle says that gravity will redshift light. So as the light shoots away from the Earth, its wavelength will get longer and longer and longer. All right? So that's one of the consequences of the equivalence principle of general relativity, is gravity will Doppler shift light. Now remember, when we did special relativity and we moved to different reference frames, we said, look, if someone gets on a spaceship and they're flying with respect to me, I'm going to perceive their heart beating at a lower frequency. They're going to perceive my heart beating at a lower frequency. It kind of worked both ways and was kind of weird. Gravitational redshift is not like that. This scientist sees the oscillator making light down here as oscillating slower, right? But if conversely this scientist were to shoot a laser beam down here, they will see it shifted to higher frequency, right? So it undoes what happens, all right? It's kind of more reversible in that sense than transforming reference frames in special relativity, all right? So now, right, the light gets redshifted due to gravity. Now, I'm going to skip the derivation of how much it gets shifted by because we're not actually working the problems in the homework, but here's just kind of a basic idea. Imagine I have two atomic clocks, one down here on the Earth, one up here on the top of the tower, all right? I link a laser beam, I lock a laser beam to the oscillation frequency of my atom, and I shoot that beam up to somebody up at the top of the tower, all right? Both of our atomic clocks, we think they're working great, but I send my beam up to them and they say, hey, your beam is redshifted. That means your clock is running too slow. And they double check everything. They say, you know, everything's fine. If the person up here sends a laser beam down, it will get blue shifted. And they will look at this light and say, no, your clock is running too fast. The real answer is gravity affects time. So if I have an atomic clock on the Earth, an atomic clock up in space, the person up in space will perceive that the atomic clock on the Earth is running too slow. Whereas the person on the Earth will perceive that the atomic clock up in space is running too fast. So gravity slows time down. All right, if you've seen Interstellar, right? They went onto this planet and gravity slowed time down. Okay, there were a bunch of other inconsistencies there that were totally wrong. But hey, the basic idea that if I have a big gravitational field, if you move down in gravity, time will slow down. So, right, to you it seems like time's traveling is normal, right? But for somebody, you know, up in space, they will perceive your clock running slower, your heart beating slower. You will perceive the person up in space having their heart beat slower, their clock, or sorry, heart beat faster and their clock run faster. Okay, and here's our free-falling observer. All right, another interesting consequence of the equivalence principle is the deflection of light. If you're a scientist on a spaceship that's accelerating and you shine your laser pointer towards the wall, the light will bend, right? Because the light's really traveling a straight path, but your reference frame is accelerating, therefore it looks to you like the light is bending, right? Well, if gravity and acceleration are equivalent, that means that if you're on Earth, the exact same thing should happen. And it turns out that light falls at the same speed as everything else, all right? Because it's not really falling, it's just following bent space-time, all right? Okay, so light falls at the same rate as everything else. This is because things don't really fall under gravity, they just follow their non-accelerating world line. And those of us who are standing on the Earth not falling, we're pushing against gravity, so we're really accelerating upwards. But the light doesn't, and the keys we let go of don't, and so they both fall at the same rate. All right, some interesting consequences of general relativity, black holes. It turns out if you get something dense enough, if there's enough gravity, light can't even escape from it. And so that's the idea with a black hole. There's enough gravity that if I have some light coming out of here, one way to think about it is, hey, light is pulled by gravity, so a black hole is something that light can actually orbit around it. Another way to think about a black hole is light trying to get out of a black hole will be redshifted by gravitational redshift out to zero frequency, and then there's no light, right? So light cannot get out of a black hole. Another interesting consequence of general relativity is gravity makes time run differently. So, Newton and Kepler, they had their orbits of the planets that were ellipses, right? And the planet just goes around the sun in ellipses. Well, it turns out that Mercury's ellipse shifts with time. It goes around in this ellipse, but over time the ellipse rotates around the sun. All right? For a long time, people thought there must be another planet out there affecting Mercury's orbit. When Einstein wrote his paper on general relativity, this was one of his proofs. He said, look, this theory actually predicts exactly how Mercury's orbit shifts. So the reason Mercury's orbit shifts is because the dynamics of an orbit depends on time, and when Mercury gets close to the sun's gravity makes time slow down on Mercury. All right? Okay, so that's basically general relativity in a nutshell. Now I'm going to show you some more cool things you can do with relativity that you don't need to know for the homework. It may even be confusing for you, so you maybe don't want to watch it, or if you do, take it all with a grain of salt. But here's just some cool things I wanted to share with you. First off, well, actually, this is pretty useful. This is a lot like the homework, but you don't have to watch it. I'm going to show you more esoteric stuff later. But imagine I have an electron whose kinetic energy is equal to its rest energy. What does that mean? How fast does an electron need to move such that its kinetic energy is equal to its rest energy? All right? So the total energy of a moving particle is just gamma mc squared, right? But that's equal to the rest energy plus the kinetic energy. All right? So the rest energy is mc squared, and the kinetic energy is then going to be gamma sub u. Gamma sub u minus 1 times mc squared. So if the rest energy is equal to its kinetic energy, how fast is it moving? That means that mc squared is equal to gamma u minus 1 mc squared, right? That means if the kinetic energy is equal to the rest energy, this is true. Well, look, we can cancel these out, and then I get 1 is equal to gamma u minus 1, which means that gamma u is going to be equal to 2, but that's equal to 1 over the square root of 1 minus v squared over c squared, right? So that means the square root, if I multiply both sides by the square root of 1 minus v squared over c squared and divide by 2, I will get 1 minus v squared over c squared is equal to 1/2. All right, square both sides. 1 minus v squared over c squared is equal to 1/4. All right, then take this to this side and that to that side, and you'll get v squared over c squared is equal to 1 minus 1/4, or 3/4, which means that v is equal to the square root of 3/4 times the speed of light. Did I do that right? If I didn't, let me know. All right. I know the physics is good. I just kind of rushed through the algebra. All right? So I could ask you, I could say, hey, how fast does an electron have to move for its kinetic energy to be equal to its rest energy? And you can solve this. I could say, hey, how fast does an electron have to move so that its kinetic energy is 10 times its rest energy? And that's basically how you do it. All right? But this kind of tells you mc squared. C is really big, right? So if I have a little bit of mass, multiply that by c squared, suddenly I have lots of energy. All right? And for an electron to have a kinetic energy which is equal to its rest energy, it has to travel almost at the speed of light. Right? That's what that's telling us. Or a good fraction of the speed of light. All right? Here's another interesting thing. It turns out in quantum mechanics we learned that there are these things called positrons. They're like electrons, except they're not. They're antimatter. When Star Trek talks about antimatter, that's real. Antimatter is real. All right? And so it turns out you can make these positrons, which is like an electron. It has the same mass as an electron, but it has a positive charge instead of a negative charge, and so forth. All right? When an electron and a positron come together, they can annihilate. They can turn their mass into pure energy. So imagine I have an electron sitting here and a positron, and they combine together. All right? Conservation, they can just turn into pure energy, a photon of light. Well, it turns out I can't just have one photon of light fly away, because these two, if they're sitting still and then they combine, they initially have no momentum. My photon has momentum, so I need to conserve momentum by having two photons with equal momentum going in opposite directions, right? Equal momentum means equal energy, so that means what I've done is I've converted the rest energy of these two particles into photon energy. How much energy will these photons have? I'll call it E sub gamma, because sometimes gamma refers to photons. Let's not do that because we use gamma for something else. E photon. How much energy will each of these photons have? Well, I'm splitting the rest energy of these two particles among two photons, so each one will have the rest energy of one electron, or 1 positron, which is the same, which is m mass of an electron, c squared, all right? It turns out, remember we talked about electron volts? You can think of the rest energy of an electron in terms of electron volts, and it turns out the rest energy of an electron is 0.510999906 mega electron volts, which means I can think of the mass of an electron, right? Rest energy is mass times c squared, so I can think of the mass of an electron in terms of its rest energy divided by c squared. So I can tell you the mass of an electron is 0.510999906 mega electron volts over c squared, and that's a unit of mass. But anyway, the energy of my photon is just going to be the rest energy of the electron, which is 0.510999906 mega electron volts. Turns out that's an awful lot of energy. Visible light has energies, photons of visible light have energies on the order of a couple electron volts. So these are very, very energetic photons of light. Astronomers can detect them coming from in space. They see these really energetic photons, and then what do they say? They say, there must be positrons annihilating with electrons, making that light. Pretty cool stuff. Okay. Oh, I already showed you the derivation of E equals mc squared. I got ahead of myself. So, lastly, I'm going to talk to you a little bit about energy and momentum transforms. So, I can calculate the energy of a particle, right? The total energy is gamma mc squared. The momentum is gamma sub u m u, which is a vector, right? Well, I can find that my particle's moving at some velocity. I can measure that in some reference frame. If I transform into another reference frame, I can find all of these because I know how to transform velocities, right? The different components, ux prime is ux minus v divided by 1 minus ux v over c squared, right? I have these transforms, these velocity transforms, so I can actually transform them and find what the momentum, the different components of momentum and the total energy are in different reference frames. But it turns out, if you want to sound really clever, remember how we did this thing where we said when I transform x, y, z, and time, if I multiply time by c, I get units of length, and I can think this is kind of one 4-component vector that transforms with a matrix, right? R prime is equal to some matrix operating on R, right? If you remember that from the previous video, it turns out you can do the same thing with energy and momentum. What you do is you make a vector with your 3 components of momentum, px, py, pz, and then if you take the total energy and divide it by c, you get units of momentum. And it turns out that this vector, all right, what should we call this? S. This momentum energy vector, it transforms using the same matrix we use to transform, that should be S, to transform position and time. Pretty groovy, huh? So the same transformation equations for position and time work for momentum and energy, as long as we think of time as c times time and energy as energy over c, so that they have the units as the same units as the other components of that vector. Anyway, groovy stuff that you don't need to know.